Thank you, Noelle.
You're welcome. Happy to have you here. Take
Thank
it
you.
away, Emily.
Thank you. Okay, I'm going to share my presentation real quick. Um, just a second. And then I am going to put it in presentation mode. And then I'm going to swap those. So, okay, how's everything visually look? Does it look okay?
Yep, it looks great.
Okay, awesome. Thank you. Um, hi everybody. I'm Emily Siedel. As Brooke said, I am Blue Hill Heritage Trust Stewardship and Outreach Associate, and that just means I support the trust in a lot of different ways wherever we might need help or needs to be met. I try to be there to support people when they need it. So just a little bit of an overview of what we're going to be going through. First, I'm just going to hit some background on myself and about Blue Hill Heritage Trust and Island Heritage Trust, and then we're going to dive into the geologic history of the Blue Hill Peninsula, transitioning to talking about geomorphology, and we'll wrap up and have time for questions. All right, so why the Blue Hill Peninsula? As Brooke mentioned, I have pretty much no credentials other than I'm a college student who really wanted to learn more about the place I was moving to last summer. I'm not George Fields by any means. I'm not a professional geologist. Just want to preface that. But I have really done a lot of extensive research just through resources that I've gathered, and so I'm really excited to share those with everybody here today. So as we said, I was an intern last summer with Blue Hill Heritage Trust, and I currently am a full-time employee. I decided to do a presentation for my geomorphology class before moving here because I really wanted to get a better understanding of the landscape and the community itself here as well. If you don't know that much about Blue Hill Heritage Trust or you're new to the peninsula or you might be moving here, I just wanted to preface that the Blue Hill Peninsula is located in Hancock County. If you're moving here from somewhere new, it's pretty close to Acadia National Park. There's a lot of amazing features here on the peninsula, geologically, and also just within the landscape itself and in the forests. And some of those notable features include bays, coves, harbors, and beaches. Here in the town of Blue Hill, we have the beautiful Blue Hill Mountain. In Penobscot, there's Walvatogus Mountain, which is also really beautiful. There's tons of blueberry fields, there's trails, and lots of different historical sites, too. So just to give everybody a sense of space, I'm primarily going to be talking again about the Blue Hill Peninsula. And for Blue Hill Heritage Trust, that encompasses the towns of Surrey, Sedgwick, Brooklyn, Blue Hill, Penobscot, Castine, and Brooksville. And then I'm going to touch a little bit on Deer Isle, Little Deer Isle, and the Stonington area, but again, primarily focusing on the Blue Hill Peninsula. So, if you're new here, there's lots of recreational activities. There's plenty of hiking, boating, swimming, hunting and fishing, you name it. It's anything outdoors is pretty much here. And then my last little bit on the trust and our work, we also offer, again, lots of hiking trails. So in the town of Blue Hill, here are some of the trails that we offer from Blue Hill Heritage Trust. And then Island Heritage Trust has a lot of trails on Deer Isle, Little Deer Isle, and in the Stonington area, as well as on some of their islands. So I just wanted to get that information out there. Okay. So before we really dive into the geologic history of the Blue Hill Peninsula, we first kind of need to understand the basics of talking about geology and what some of these terms mean, because I want to make sure it's not uber scientific and everybody can understand what I'm talking about. So with geologic time, we use what's called the geologic time scale, which is basically a system for organizing the history of Earth into units of time. A lot of these units of time are characterized by mass extinction or increases or decreases in certain biodiversity. With most things in science, we start big and then we work small. So it's the same thing when we're classifying time in geology. So our biggest time segment, which you can see on the left of your screen, which you have the Phanerozoic, which is kind of going vertically down. So we start with our eons, which are our biggest chunk of geologic time. And then we go into eras, periods, and epochs, or some people call them epochs. And so I just want to let you know a little bit of the history that goes into each of those time classifications. So if you see under, so for the eons, we have the Precambrian eon, which isn't listed on this time scale, but that pretty much encompasses what you see as the Hadean, the Archean, and the Proterozoic that are listed there. So those kind of get globbed into what's called the Precambrian eon. And during those times, during the Hadean, Earth's history had a lot of intense heat and volcanic activity. That was about 4.6 to 4.0 billion years ago. So long ago. So crazy to think about time that massively. And then in the Archean time, we had continents and simple life forms started to begin. So that was about 4 to 2.5 billion years ago. And then we get into the Proterozoic, which is where we start to see multicellular organisms appear. And that was about, this is a really like broad spectrum of time, not that billions of years ago is it, but from 2.5 billion years ago to 541 million years ago. So that's a really big gap for multicellular organisms to start to exist. So those are our eons, and again, within those, we have our eras. So we just talked about the Precambrian eon, and now we're going to get into the Phanerozoic eon, and specifically the eras that go with that. So you have the Paleozoic era, the Mesozoic era, and the Cenozoic era. And those are broken down even further, again, into periods. So in the Paleozoic era, that's where you see a lot of your first fishes come to play, amphibians, reptiles, dinos, and also you see the first forests and mass extinctions start to appear in geologic time. And then in the Mesozoic era, that's where we start to see birds, mammals, and the continents that we know today begin to form. And also the Mesozoic is really a time that people know as the time of the dinosaurs. And then finally we get into the Cenozoic era, which is where we have the evolutions of humans, further evolution of mammals, and modern day ecosystems that we have now. And so as you can see, those eras are then broken up into periods, which I won't go into too much detail about those currently. And then if you look up at the top, Cenozoic era, you have the Quaternary and the Tertiary period, and then those are further broken up into epochs. So yeah, that's a little bit about the geologic time scale, and that'll be relevant to the rest of our conversation later. There's a lot of applications for it as well. You can use it to age and date rocks and fossils. We can correlate rock strata using this. It's really good for resource exploration if you're like trying to mine a resource or extract oil. Also good for climate change studies to see how the climate has changed over time, evolutionary biology, and archaeology. So it's really neat, and I think it's important to know. And it's a good basis for anything geology-wise when we're talking about geology. Okay, so now we're going to get into the geologic history of the Blue Hill Peninsula a little bit. And so I just want to preface saying that the geologic history here is simple but complex at the same time. It's simple in the sense of the same thing was happening over and over again, but it's complex because nothing's ever truly simple. And so during the late Proterozoic, so if you wanted to, actually I'm going to go back real quick, if you want to take a picture on your phone of the geologic time scale, just to have that as a reference as we're talking, you can go ahead and do that. I'm going to give you like 30 seconds. Awesome, great. just so that way we have the basis of what we're talking about here. So a lot of Maine and specifically the peninsula's geology and all these mountains and rock outcrops that you see are primarily from what we call orogenies, which is a process of mountain formation in which tectonic plates typically collide or when they're moving away from each other, generally with collision. So you have a lot of thrusting, which is where plates collide and one plate moves up. You have a lot of folding of rock, so that's when the plates collide and the rock kind of starts to bunch and get a lot of folds and waves in it. And then faulting, metamorphism, and platonism, which I'll talk more about as we continue to go through this presentation. So in the late Proterozoic and late Proterozoic and then the early Paleozoic eras, we have the foundations of Maine being formed. Primarily, you have a lot of sediments there, and igneous and, so you have a lot of sediments that are the basis of Maine, and then we get into the early Paleozoic era, and we start to have an orogeny, so two plates collide, right? And so we have the Penobscotian orogeny, which happened during the Cambrian era, and that is also when Blue Hill Mountain was first formed, which is super exciting because that's a feature that we know very, very well here on the peninsula. And so we have, from the late Proterozoic and early Paleozoic, mud, sand, limestone, marine sediments, volcanic ash. They were deposited in an early ocean known as Iapetus. So then we get into the early Paleozoic era, and we have a series of those orogenies. They result in what's called deformation, which is folding and faulting. It's another word for that. And low-grade metamorphism. It's specifically a subduction zone, so kind of like what's happening in the West Coast right now, where we have one tectonic plate and another colliding under it. So where they collide, kind of where my fingers are touching my wrist, you have a lot of volcanic activity happening right on that border. And so with that, we get to see a lot of igneous intrusions and stuff like that. So specifically with Blue Hill Mountain, it's part of the Ellsworth Schist formation, and it has a contact with the Lucerne granite, and I have a visual tool to help us with that. So heat from magma, so we have magma that is underneath these plates when they're colliding because there's a lot of heat and temperature there. So magma is basically being baked and toughened by the rock enough that it better resists other mountains nearby. So Blue Hill Mountain exists, and it's not as weathered as some other mountains you might see because of that tectonic activity that was happening specifically during that time. Then we get into the middle Paleozoic era, which is a really, really explosive time for volcanism, specifically during the Ordovician and Silurian periods. So we just had a lot of volcanic activity, and then we kind of see this pattern of volcanic activity, marine sediment deposition. And so that happens here in the middle Paleozoic. We get deposition of more marine sediments, sedimentary rocks become slopes since there was so much faulting and volcanic activity. And then the end of the middle Paleozoic is characterized by the Acadian orogeny. And this is the collision of the North American plate and the European/African plate. We have lots of high-grade metamorphism. We have lots of mountain building happening there. And then at that time, sediments, so the sediments that were deposited during the Silurian period, end up getting buried up to 9 miles, like below mountains. So that's a lot of energy, lots of temperature, high heat, high pressure. And then kind of continuing on, we get to the late Paleozoic era, and we have a lot of faulting, and not too much to say about that. Very similar, again, to what's happening on the West Coast with earthquakes. So if you can imagine a lot more earthquakes happening during that time, maybe not so much volcanic activity, but we get a lot of uplift. So the plates are faulting, and when that happens, they kind of strike past each other, and maybe one tectonic plate might go above or under the other. So that's where we get that uplift. And then we also get a lot of erosion happening during the end of the late Paleozoic era. And then going into the Mesozoic era, the Atlantic Ocean starts to form. So we have those plates that were already converging away or diverging away from each other are kind of ripping apart bit by bit, inch by inch, little by little, year by year. And eventually we end up getting to our current, the way the Earth looks currently, which is kind of pictured in this diagram on the right. And you can see some of the bigger tectonic plates and where they are today. If you ever get the chance to try to find a visual of that can show you, like an animation showing you how the tectonic plates have moved over time, it's super duper cool. Okay, so here's a little bit more on mountain building, since that's what we know and love about Maine specifically. So here's some better diagrams explaining what I was showing with my hands on the camera, if you could see that. So the first diagram we have for mountain building is continental to oceanic conversion. So here, oceanic crust is thicker and denser than continental crust, so it goes under, like it submerges, not submerges, but it subducts underneath the continental crust. And you can kind of see where I was talking about with the magma cooling and the volcanic activity that happens right where that border is. And then on the right, we have a continental convergence. And so here we get a lot of uplift because they're either the same density, or if they're different density, which might happen if one tectonic plate for continental plates are older, they're typically denser, so those would be subducted instead. And so I've mentioned a lot of igneous activity. So we have igneous activity and we have metamorphism. That's common themes you're going to hear throughout this presentation. And so this bottom diagram, it looks really chaotic. I know. But I just wanted to point out on the bottom right, kind of where my mouse is, if you can see that, at Carter Nature Preserve, which is one of our properties, you can see a lot of dikes, which are essentially when magma shoots up and cuts through vertically a column of rock. And then we also will see sills, which is where a dike ends up cutting up vertically through rock, and the sill is kind of like your windowsill. It's magma intrusion, and it sits horizontally instead, which is really, really neat. So I just wanted to mention that. And then also in geologic time here on the peninsula, we've seen a lot of stratovolcanoes. So if you shift your attention to the bottom, or the top left of the bottom visual, we had a lot of stratovolcanoes here as well. And we know that because we have evidence of rhyolite, which is a type of igneous rock that cools super duper fast. So it ends up having very small grain sizes. And we can see that as well at the Carter Nature Preserve property. And so that's evidence of those volcanoes. So just to get everybody thinking, because that was a lot of diagrams and a lot of words all at once, but just want to have you picture like your favorite mountain or your favorite viewpoint on the peninsula or on Stonington or Deer Isle, and just think about that. So I have some photos here from some of my favorite places. So we have Blue Hill Mountain, we have Lookout Rock, and then the bottom photo is from Walmatogus Mountain this winter. So just some pretty photos, so that way I'm not just talking at everybody. And then this is a really cool visual for understanding granitic plutons. So we talked a lot about those igneous dikes. So another igneous feature that you will often see are what are called plutons. And so a pluton is basically when you have magma and then it cools underground, and it takes a long time to cool. It's pretty far beneath the Earth's surface. And so you can see where my mouse is kind of near. So this is MGI. And if you come over here, you'll see the Blue Hill Peninsula has one of these major granite plutons that is the bedrock for part of it. And then here's just another visual if you're curious like what kind of rocks we have here. There's a lot of the upper Precambrian to middle Ordovician rocks, which is really neat because that means pretty old. We have a lot of ancient rocks here, which is super awesome. I'm going to come here. And then this is a bedrock map of Maine. You can find this on the USGS website. I have it as a resource at the end of this PowerPoint if anybody's interested and wants to learn more. So I'm going to go through all these colors because there's all this rainbow of colorful rock. There's a lot happening on the peninsula geologically time-wise. So we kind of have this bubblegum pink up near Penobscot. And so the bubblegum pink is called the Penobscot Formation, and it is from the Ordovician period. And then we get into this light pink that's kind of in the top corner of Penobscot, and this is known as the granite of Wallatogus Mountain, and it's Devonian in age. And then we have this salmon over here, which is it's called the granite of Gray Ridge, and it's also Devonian. And then as we move closer to Castine, we'll have some what's called the Castine volcanics, which just means that there are irregular beds of felsic and mafic volcanic rocks. So it's a lot of random igneous rocks there. And then in kind of like the slimy green of Castine, we get into the Islesboro Formation, which is very, very old rock. We have the Cambrian to the later Proterozoic in age, which is kind of really cool. And then I'm kind of shifting like across the map, just explaining everything. So we have like these purples and these grays, which represent plutonic rocks. And then we have, like as I'm moving, I'm going to shift a little bit to Brooklyn. So we have this light gray at the very bottom of Brooklyn, which is called the Oak Point granite, and it's Devonian in age. Then there's this burnt orange that encompasses a lot of Brooklyn and Blue Hill and parts of Surrey, and that is part of some, that's the Ellsworth Schist. So everybody's probably familiar with that. I know a lot of people talk about Ellsworth Schist and Lucerne granite, as well as the Stonington granites, which I'll talk a little bit about as well. Then we have like this regular orange kind of encompassing this trio around Blue Hill. So we have the burnt orange, which is the Ellsworth Schist. Then we have this regular orange, which is just some Devonian granite. And then we have this light orangish yellow color, and that is the Lucerne granite that I had just mentioned. And then this olive green that's encompassing Sedgwick is a type of Silurian granite. So I know that's a lot, but I just want everybody to kind of have an understanding of the hodgepodge that really does build the Blue Hill Peninsula. And then for Little Deer Isle and Stonington, we have some of that blue, which again was the Castine volcanics. And then we have more of the Ellsworth Schist. We have some of the Silurian granite. And then there's that light gray again, which is the Oak Point granite. And then encompassing like most of the Stonington area, you will often find the Stonington granite. And a place that's really good to see that is the Settlement Quarry. If you've been up to that IHT property, it's really beautiful there. And so a lot of stone was mined and quarried from there, and it's been distributed all over the world. It's in New York City, it's in California. I know I've heard that it's in Europe. Really, really cool. I actually just went to New York City a few weeks ago, and my friend and I were walking around, and we saw like evidence of the Deer Isle Stonington granite on some of the sidewalks, and it was really, really cool. And then there is still an active quarry on what's called Crotch Island there. It's one of the only active quarries still. Okay, that was a lot, but now we're going to dive into understanding rocks and minerals. just because there is a little bit of a difference before I get into talking more about granite and schist. So the difference between a rock and a mineral is that a rock is basically just composed of minerals, and a mineral is a naturally occurring inorganic element or compound. So basically, it's something that's not living, that has internal structure. It has characteristic, like chemical composition, that's pretty well established, set in stone, if you will. It has crystalline form, and it has physical properties that you can use to identify it. And this can be any naturally forming inorganic material. So a lot of people will ask the question, oh, is ice a mineral? Yes, ice is technically a mineral because it has an internal structure, it has a very specific chemical composition, it has a crystalline form, and it has physical properties that we can identify it with. So there's a fun fact for the day, if you didn't know that. So now we're going to dive a little into the rock cycle, because I think it's important to understand the metamorphic rocks and igneous rocks that are around us. And we're going to talk a little bit about those differences today. So you'll see visually here we have the rock cycle. And primarily, like I said, we're going to talk about metamorphic and igneous rocks. So with metamorphic rocks, in order for metamorphic rock to be formed, it's essentially its parent rock is either a sedimentary or an igneous rock. Those are pretty much the only options it's got. So those are its parent rocks. And what happens is you have a lot of like those tectonic orogenies that I talked a good bit about. And so with those orogenies, you get a lot of high temperature and high pressure. High heat, high pressure. Those are the most important things when it comes to metamorphism and forming metamorphic rocks. And then you have different grades of metamorphism. And so we'll talk a little bit more about that later, but with those grades, you have high-grade metamorphism and low-grade metamorphism. And whenever a rock is metamorphosed, the minerals within that rock can not necessarily change composition, but they change chemical structure and might eventually become a different mineral. And so you see that a lot with schist and gneiss, which, again, we'll continue to talk about as we go along. And then, so we said metamorphic rocks are parent rocks from sedimentary and igneous rocks. Igneous rocks themselves are characterized by melting and then crystallization or cooling. And you have intrusive cooling and extrusive cooling, which isn't represented on this diagram, but I think that would be really cool to mention if it could. So intrusive, it has to deal with magma, so it's magma cooling underneath the Earth's surface, and when that happens, you get bigger crystals. That's where you get a lot of granite formation, and then you have extrusive igneous rocks, which are from lava, and those cool really quickly, and they have small, barely any crystals, if any. Okay, so now we're going to dive into the differences between schist and granite. We don't have the chat open, which is okay, but if people want to put feedback into the Q&A, I think that will work for this. So I'm just curious, who thinks what rock is what? So there's a picture of a rock with a glove, and there's a picture of a type of rock with a nickel located in the bottom left corner. And so I'm just curious, which do you think you could like put glove dash if you think it's igneous or metamorphic? Wait a little bit for some responses. Okay, nice. Okay, we're getting some good feedback. Okay. So, yeah, so the photo on the right is actually metamorphic. And it's metamorphic and because it's lacking a lot of those bigger minerals that you might see when it comes to an igneous rock. And so it's primarily composed of mica. So the photo with the glove is actually a photo of the Ellsworth schist. And you can see a lot of the folding that I had mentioned previously in that rock. And so that is also a giveaway for that it might be metamorphic, is when you see a lot of those folding and banding and waves. And then for the granite on the right, it's actually the Lucerne granite, which is igneous. So that means that it is a parent, it could have been a parent rock for the schist on the left. It's not, but it could have been. And so schist, specifically the Ellsworth schist here, is primarily composed of micas, and that's a type of mineral. They're very shiny. They're very high in silica. Some names of those mica minerals include muscovite and biotite. And then for igneous rocks, their mineral composition is typically feldspar. So you have plagioclase feldspar and alkali feldspar, which I could show you if I had like a hand lens. And then granite is also characterized by quartz and again by mica, specifically biotite. And then there's another mineral called hornblende that it's primarily characterized by. That's where you get the black flakes in it from. And they can all metamorphose into gneiss, which I won't end up talking as much about as I wanted to. So for schist, primarily it becomes metamorphosed from shale. Shale is a sedimentary rock. And so I like these diagrams because you can see how the temperature and pressure might affect the metamorphism of rock. So if we start out with shale, which isn't pictured on the diagram on the left, unfortunately, but if you start out with shale, that is its primary sedimentary rock. And then as you increase heat and pressure, you get a slate, and then it transitions to a phyllite, and then you get to your schist that we're all familiar with. So schist is a very mid metamorphic rock. It's not the lowest of temperature and pressure, but it's not the highest of temperature and pressure. And so if we were to keep going, schist, which you can see some like flakes of mica in still a little bit, would metamorphose into gneiss, which has these bands across it. And so the quartz and the mica that are semi-prevalent in the schist end up kind of forming those white bands, and then the biotite and hornblende that I had mentioned that are like the black minerals you might see end up forming those darker bands. So it's really neat. It's cool to see and think about. Okay. Alrighty, so that was a lot in terms of geologic history, but now we're going to go and transition into the geomorphology. So as Brooke had mentioned earlier, geomorphology is the science of studying landforms, like trying to understand what they are, describe landforms, understanding their origin, how they came to be, and also their relationships to structures, and basically how the history of the landscape has changed over time. So with that, primarily here in Maine, we have glaciation, which is so fun. We love learning about the glaciers, and then a lot of coastal features. So some characteristic features of glaciers are deltas, moraines, lakes, eskers, and erratics. These are some things that you might be familiar with and heard of, just talking to people, thinking about agriculture, thinking about quarry mining, stuff like that too. And then some coastal features we'll talk about are bluffs and beaches. Okay, so glaciers, yay! So what is a glacier? Like, this is something we don't always think about. We have to define the things before we talk about them. That way we actually understand what we're seeing and what we're processing as people. So a glacier is a large mass of ice, right? A big block of ice, formed on land by the compaction and recrystallization of snow. It typically has a downward slope just due to its own weight and gravity. If we think about the forces of gravity pushing down on it, that's a lot. That's a lot of pressure, right? And so something I just want to mention is that glaciers are both destructive and constructive. So they are destructive in the sense that if my elbow is the back of the glacier. They pluck rocks from the back of the glacier, or underneath. So they're plucking rocks from the ground, and then those rocks tend to move because there's water flowing under a glacier. So sometimes glaciers can be referred to as rivers of ice as well, because water is constantly flowing under them. And so once those big rocks are plucked from the underneath, they end up being flowed out, and as the glacier melts and recedes, those become deposited. And we'll talk a lot more about those depositions as we continue on. So you have continental glaciers and alpine glaciers. Basically, continental glaciers are glaciers that have been formed on continents. And so that's a lot of the glaciers that's actually all of the glaciers that have affected the Blue Hill Peninsula, Maine, and most of North America are all pretty much continental glaciers. And so again, glaciers are things of destruction and construction. And so they're mechanisms of erosion, so they erode away from the landscape. They transport those deposits, or they're not deposits at that point, but they transport those goods, if you will, rocks, minerals, till, soil, sand, gravel, clay. They transport all of that down, and then it becomes deposited. And so what's really neat about Maine is that during the glacial period here, the last glacial period was during the Pleistocene epoch, which is about 2.5 to 10,000 years ago. So the last of the glacier receded from Maine and North America pretty much about 10,000 years ago, or at least the United States, what's considered the United States today. And that was known as the Laurentide ice sheet. And it caused a lot of depression and subsidence of coastal Maine, which is so neat to think about. So all of that weight and pressure we were talking about, that causes a lot of friction on the ground or on the earth. And so it caused what we call depression. And so it depressed, like that weighed enough that it actually depressed the continental plate at that time. And so we see a lot of deposition of marine sediments along coastal areas here. And so some of those glacial features that we'll talk about and you might see on the landscape are generally produced from what we call glacial marine sediment formations, because Maine was underwater during that time. And so the graphic on the right here is really cool because you can actually see how far the water came up. So there's a bullet point marked as Bangor. And so you can see like where the present day land surface is and how that's been changed over time. So I really, really think this is cool. So we had the depression, and then as the glacier receded too, we get rebound. So then the earth comes back up, and that could be lots of miles. I think it says like the glacier itself, the Laurentide ice sheet, was 1.5 to 2 miles high. So that's how high the ice sheet was, and I'd say the continental crust came back up a little bit less than halfway up from where the glacier was covering. Here's another really cool diagram I like to show just the processes that are at play whenever all of these glacial marine sediments are being deposited. So you can see here where the till is being transported. We call till, which is like a mixture of gravel and sand primarily. It's not very well sorted, meaning it's kind of all globbed together. It's not like sand is underneath or gravel is above. And so you can see the deposition of till and how the glacier might have worked underwater. And so this is a glacial marine, what we call a morphosequence. And a morphosequence is just a fancy word for saying a group of glacial deposits, again, primarily sand and gravel, that were deposited around the same time. And specifically, they were deposited by the meltwater streams of a glacier. And so we see that here, the gray just represents bedrock. Then we have kind of this orange, which represents that glacial till that we saw in the previous diagram. And then the yellow is sand and gravel that's been deposited in different landforms, such as moraines, fans, and deltas. And yeah, and then the purple here is those glacial-marine sediments or glacial-marine mud, specifically the Presumpscot Formation. Okay. Alrighty. So this is just another really cool visual to show like how far the glaciers came up to Maine, and it's honestly kind of close to Millinocket, which is like wild to think about. So, okay. So some evidence of glaciers we can see today. Again, I've mentioned glacial till a lot, and as I said, glacial till is basically an unsorted, or we call it unstratified mix of clay, silt, sand, gravel, and boulders. So it's a wide variety of things, and you can find that pretty much anywhere here in Maine. A lot of your fields that you've been in, your blueberry fields, have glacial till. Some other things you might see if you're like walking on, I'm just thinking of Carter Nature Preserve because I was out there yesterday. So at Carter Nature Preserve, if you see like really exposed rock outcrops, sometimes you can see grooves in the rocks. Those are called striations, and those are formed from the friction of intense pressure and weight of a glacier moving across those rocks at one point in time, which is really cool to think about. And then another thing that we can find evidence of glaciers, like how do we know they existed, is just the terrain itself here. So we have what's called hummocky terrain, which basically just means there's lots of small mounds or knolls within the landscape. And I have some pictures to show that. And that really helps pronounce the pit and mound topography of Maine. You might have heard about that a little bit, specifically with Maine's forests. And so that really, the hummocky terrain helps accentuate that. So the first photo we have here is actually called a till stone. And so you might find a stone that's small, kind of bullet, not small, but it might be smaller than like a glacial erratic or a giant boulder, smaller than a boulder basically, probably about like yay big. And they'll be faceted, kind of like bullet shaped, rounded, and they actually might have scratches from the glaciers on them. And then the second photo is just showing striations. Third photo, I'm moving from left to right, shows glacial till, which is very prevalent here. I remember I had to dig some post holes last fall, and I was trying to dig holes in glacial till, and it was not going very well for me. And then the last photo on the right is of hummocky terrain, just so you can kind of see those like knolls and mounds and how it really accentuates the pit and mound topography of Maine. So, kind of mentioned previously, deltas are other really prevalent features of glaciers. So that includes piles, basically a pile of sand and gravel that was deposited by the outflow of running water. So under the glacier, we have that glacial deposit, running water into a slow-moving water body. So that could be a lake or a wetland that was being formed from a glacier. And so there's just some really cool examples of that. We also have moraines, which is where a lot of our blueberry fields here in Maine are. And the glacial till is one of those things that actually like blueberries love. And so as much as we might curse and throw our fists at glacial till for making our lives a little difficult for construction or for digging post holes, in my case, they are what glacial till is really what accentuates our blueberry fields and allows blueberries to grow here. So the photo on the left and on the right are both at Sedgwick, the blueberry barrens there. So really cool. And moraines themselves are just mounds or ridges of glacial drift, again, typically till, and those are usually deposited at the end of glaciers. So a glacier might be melting, it'll stop for a little bit, and then you'll have a moraine be deposited at the end of there, and then it'll start melting again, and then you'll have what are called recessional end moraines, or just terminal moraines. So like where it was the furthest the glacier exceeded, and then also where is the last place it receded to as well. So yeah. And then we have some glacial erratics. You might recognize some of these if you did our beautiful Boulders Challenge back in 2020. I scoured that whenever I was moving here. And so George and I were just talking about this morning, and they're really cool. Does anybody have any guesses where some of these erratics might be? Let me see here. Okay, so the first erratic on the left is actually at Penny's Preserve. And then the second picture is of the Kingdom Woods Conservation Area, specifically Turtle Rock. And so Turtle Rock, I would not personally consider an erratic. So an erratic, because we have to define things to understand them, is a rock fragment that's been carried by glacial ice, and it's been deposited a distance away from its original outcrop. That could be like 5 miles, that could be over 1,000, over 100,000 miles. That distance is not specified. Basically, it's been transported some distance away from its original outcrop, its original parent rock, and it then is resting on a different type of bedrock or a different type of lithology. And so Penny's Preserve, the first one, is the granite of Blue Hill, is Devonian, specifically the Lowstern granite. And then at Kingdom Woods, Turtle Rock, I would not consider an erratic, just in the sense of it hasn't moved very far, like it hasn't moved miles away from where its original rock is. It's still sitting on its same parent bedrock. And then the final one is from 100 Acre Woods, and I would consider that one an erratic. And I just want to note what's really neat about this area is that a lot of the erratics have only moved about, I'd say like 5 to like max 10 miles away from their original parent bedrock, whereas like in Pennsylvania or in New York, the glacial erratics you'll find there actually is from Canada, and they've traveled like hundreds of, like thousands of miles. So it's really interesting to think about like how much energy and effort had to go into that glacier, picking it up and moving a rock. Specifically for these ones, they didn't go very far, but for a rock to get from Canada all the way to like Pennsylvania or New York is pretty impressive. Okay, finally, we're going to talk about some coastal features you might see, and these are also geologic processes that are happening modern day because geology never stops. So on the Blue Hill Peninsula, you'll find a lot of bluffs, which a bluff is a steep shoreline slope formed in sediment. It's composed of loose materials like clay, sand, gravel, and it has to have 3 or more feet of vertical elevation above the high tide line to be considered a bluff. And so a big misconception is that cliffs or slopes and bedrock, so you might have a rock ledge, some people might call those a bluff, but it's not. And a lot of the erosion of bluffs depends upon specific materials, like the materials it's formed from and the vegetation. Sorry, I didn't mean to go. But I just want to point out that the top photos are highly unstable bluffs. The middle photos are highly unstable and a stable bluff. And then the bottom photos are stable and not stable bluffs. And so this is just a map showing a lot of the bluffs in Blue Hill Harbor, and I like it because I like that it says like highly unstable, unstable, or stable bluffs, because these are the processes that are happening today, and it's just cool to see geology in action. And then finally, one of Maine's best coastal features that we're known for are the beaches here. Again, most Maine beaches are typically very, very rocky. Some are rock ledges, others are cobbles that have been deposited by glaciers, and very rarely you'll get some truly sandy beaches, and that primarily is just dependent on those glacial marine depositions that we were talking about previously. So I want to say thank you so much for everybody for listening. If you are inspired by this and you want to continue to go around the peninsula and see what you can find, here's just some things that you might want to have with you in the field if you're out exploring. It's always good to have a field notebook with you just so you can write down your observations. Hand lens, which so that way you can see some smaller minerals and rocks and look closely at rocks, or even if you're out and about and you want to look at plants and ferns and other like sorts of bugs and insects, is a really handy tool. If you're out for rocks, I always recommend a rock hammer. They're great. Might be kind of tricky here with all the quartz since it's a very hard mineral, but you can always give it a go and try and see if you can chip a bit off. Always have your camera or your phone, something to take pictures, and whenever you're taking pictures, you always want to have something that you know you can reference for size. A field notebook is really good for that because you know it's 6 by 4 inches. And then I always recommend you bring a bag of some kind with you so that way you can collect your rocks and take them home with you. And then it's always good to have a reference book, and a snack and a good adventure buddy are always essential as well. Okay, thank you so much for listening. Overall, I just want to say rocks are cool, and the Blue Hill Peninsula and Stonington Deer Isle, again, I just want to rephrase, have a simple but complex geologic history that are shaped by orogenies and tectonic activity as well as glacial and coastal processes, and they've shaped our lives a lot. So I hope I can see you all out in the field hunting for rocks as well. Here's some of my references, and then I have more resources if anybody's interested in some books or dictionaries, and then there's some apps you can get on your phone too, just to know where you are geologically in time. Thank you. Are there any questions?
Yeah, thank you so much, Emily, for that wonderful presentation. As you know, I'm definitely an novice when it comes to geology, so it's really fun to learn something new about the peninsula and Maine in general. So yeah, now we can open it up to audience questions. As Noelle mentioned, we have that Q&A box at the bottom of the screen. You might need to just hover your mouse over it and it'll pop up there in the middle. Go ahead and pop your questions in the Q&A and we can relay them to our speaker.
First question that came in from Lisa. Hi, Lisa. Where can we find an esker?
Oh, good question. So I do want to define an esker because I mentioned it and then I just kind of breezed past it. So what is an esker if people are wondering? An esker is basically, it's like a serpentine shaped ridge of really roughly stratified sand and gravel it's deposited subglacially, so kind of within the glacier, and it's left behind once the ice is melted. So it kind of looks like a river in a way. We were talking about how glaciers are rivers, and so it's a serpentine-shaped ridge, just full of really not well-sorted sand, gravel, and silt. And so you can find an esker in Ellsworth, actually. There's the Ellsworth esker there, and I believe there's actually a hiking trail that goes past it. And then I could be wrong about this. Please don't. You can do some research. I can do more research and follow up with you afterwards, too. But I believe that there's an esker closer to the Belfast area as well, too.
Awesome. I can handle the next question. So how can we find the list of references, or how can we get your list of references if we don't have our phone with us?
Yeah. So this PowerPoint, let me think. So I can add the PowerPoint, I think, to the YouTube video whenever this is posted, and I can list those references in the YouTube video posting. And then if you want, I can also go back on the slides so that way you can jot them down real quick. So I will do that in case, yeah. So now they're on display for everybody. If you want to write them down on a piece of paper or something, feel free to.
It seems like we have a lot of large erratics on the peninsula. Is that true?
I would say, yeah. I think they're pretty big. So for some, I would say they're big, but also size is dependent on what you're referencing. So we have some pretty big erratics here, but if you think about like the biggest erratic in Maine, I can't remember its name right now. I'm sorry. Again, I'm pretty new to Maine and the peninsula, so I'm still learning. But George and I were talking about this morning. The biggest erratic in the state of Maine is like super huge, and for it to be, it's broken up into like chunks bigger than some of the erratics that we see here on the peninsula. So that's like the biggest glacial erratic. I would say they're pretty. I'd say they're like large in size. I wouldn't say they're the largest erratics out there, but compared to some of the erratics again that you might see in like upstate New York and in Pennsylvania, because they had to travel further distances, they'll probably most likely be larger. Yes, thank you from Beth. Daggett Rock, thanks. I couldn't remember its name right now. So Daggett Rock is the biggest erratic in the state of Maine. And so it's all relative to location and also how far was it transported by the glacier? How big did it have to be to just be plucked and dropped somewhere 5 miles away? How big did it have to be plucked and dropped thousands of miles away from where it's found? Or its parent rock, I guess.
So Emily, what is your favorite rock?
Oh, such a good question. My favorite rock, I have to ponder. I could tell you my favorite mineral. My favorite mineral is fluorite because it comes in lots of different colors. My favorite rock itself, I love a good sedimentary breccia. It's like, it's a type of conglomerate, and it's got a lot of like broken shards and pieces of other rocks in it, and it's super cool. Look it up. It's BRECCIA, breccia.
Awesome. So we'll take a couple more minutes to see if anyone has any additional questions for our speaker, but it is 5 p.m. So if anyone does have to head out, that's fine. I just want to remind everyone that this is actually being recorded and it will be on our YouTube page shortly. And you can also view previous Friends from the Field presentations on our page as well. Friends from the Field is going to take a break over the summer, but we will return in the fall. So please look for our events and come to those whenever you can. As always, they will be free. We've got some nice speakers lined up for the future as well. So again, I think we'll give a couple more minutes, but I want to thank everyone for joining us today. We really appreciate you coming to learn from Emily with us today. And oh, do I see a hand raise pop up?
I don't see anything.
Oh, maybe not. Sorry about that. But yes, if you do have a question, just go ahead and write it in our Q&A. And so again, thank you for being here. Thank you, Emily, for your presentation and for sharing all of your knowledge with us. Thank you, Noelle, for all of your help and your assistance with co-hosting.
Thank you, Brooke.
And yes, if you have to head out, we'll see you again in the future. Thanks so much, everybody. I'm going to stop recording.
Everyone. Thank
Bye.
you.